Hi everyone, welcome back to Chem Story. Today we're starting Chapter 8, and we'll be talking all about alcohols. We're going to explore their structure, the way they bond, what their shape looks like, and how polarity affects how they behave. By the end of this lesson, you'll have a clear idea of how bonding and geometry influence the properties and the reactivity of alcohols. Alright, let's get started. Let's start with the basics. An alcohol is an organic compound that has a hydroxy group, that's the OH group, bonded to a carbon atom. But not just any carbon. It has to be sp3 hybridized, forming 4 bonds arranged in a tetrahedral shape. So if the OH is attached to a carbon that's part of a double bond, like in alkenes or aromatics, that's not a typical alcohol. To count as a true alcohol, the OH has to be connected to an sp3 hybridized carbon. Now let's take a closer look at the structure of alcohols. The oxygen in the OH group is also sp3 hybridized, just like the carbon it's bonded to. That means it forms 2 sigma bonds and holds on to 2 lone pairs of electrons. Because of that, the shape around the oxygen isn't linear. It's bent, kind of like the shape of a water molecule. So overall, the bond angle is around 109 degrees, which fits with the typical tetrahedral geometry. And this geometry has a big impact on both the physical and chemical properties of alcohols. Now let's look at a couple of special cases, phenols and enols. At first glance, they look a lot like alcohols because they also have an OH group. But here's the key difference, that OH is attached to an sp2 hybridized carbon. That means the carbon is part of a double bond, or in the case of phenol, part of an aromatic ring. So even though they look similar to alcohols, that one difference in hybridization makes their properties quite different. Next, let's talk about how alcohols are classified. The key point here is the carbonyl carbon. That's the carbon that's directly bonded to the OH group. We look at how many other carbon atoms are attached to that carbon, and based on that, we divide alcohols into primary, secondary, or tertiary. If it's connected to just one other carbon, it's a primary alcohol. If it's connected to 2, it's a secondary alcohol. And if it's connected to 3, we call it a tertiary alcohol. This classification is really important because it affects how the alcohol behaves, especially in reactions like substitution and oxidation. Here's a good example that shows all 3 types of alcohols in a single molecule. If you look at this structure, you'll find a primary alcohol, a secondary alcohol, and a tertiary alcohol, each in a different position. The primary alcohol has its OH group on a carbon that's only bonded to one other carbon. The secondary alcohol is connected to a carbon that's bonded to 2 other carbons. And the tertiary alcohol, that one's on a carbon that's surrounded by 3 other carbon atoms. Now, these differences aren't just for classification. They actually help us predict how each alcohol will react in different situations. Now let's move on to the physical properties of alcohols, and we'll start with intermolecular forces. Alcohols are polar molecules, which means they have a strong dipole moment. That polarity comes from the difference in electronegativity between oxygen and hydrogen, and also from the shape of the molecule itself. Because of this, alcohols can form dipole-dipole interactions, and more importantly, they can form hydrogen bonds. And that's a big deal. Hydrogen bonding makes alcohols behave very differently compared to nonpolar molecules. Now here's something interesting about hydrogen bonding. Not all alcohols can form hydrogen bonds equally well, and the reason is steric hindrance. Primary alcohols have more open space around the OH group, so other molecules can easily get close and form strong hydrogen bonds. But as you go from secondary to tertiary alcohols, the bulky R groups around the OH start getting in the way. That makes it harder for other molecules to approach and bond. So overall, the more crowded the area around the OH, the weaker the hydrogen bonding. That's why primary alcohols usually form stronger hydrogen bonds than secondary or tertiary ones. Alright, now let's talk about boiling points and melting points. When you compare alcohols to similar-sized hydrocarbons, their boiling points are much higher. And the reason's pretty straightforward. It's because of hydrogen bonding. Since those strong intermolecular forces take more energy to break, alcohols need more heat to boil. Their melting points are higher too, though the difference isn't as dramatic as with boiling points. And here's a simple trend to remember. The more hydrogen bonds a molecule can form, the higher its boiling point tends to be. So when you're comparing alcohols, stronger hydrogen bonding usually means a higher boiling point. Let's take a second to compare alcohols with some similar compounds, like alkanes and ethers. In this example, all three have about the same molecular weight, close to 60, but their boiling points are completely different. Alkanes only have van der Waals forces, so their boiling point is pretty low, around 0 degrees Celsius. Ethers have both van der Waals and dipole-dipole interactions, which bumps the boiling point up a bit, to about 11 degrees Celsius. But alcohols? Thanks to hydrogen bonding, their boiling point shoots all the way up to 97 degrees Celsius. That's a huge difference, and it really shows just how strong hydrogen bonding can be. Last but not least, let's talk about solubility. Alcohols are generally soluble in water, but it really depends on the size of the molecule. If an alcohol has fewer than 3 carbons, it's usually completely soluble. But once you get to around 4 carbons, things start to depend on the structure. For example, tert-butanol is fully soluble because it has a compact, branched shape. But N-butanol is more linear, and its solubility drops to about 8 grams per 100 grams of water. And once you hit 5 carbons or more, solubility drops off fast. They're barely soluble in water. So in the end, both the size and shape of the carbon chain really affect how well an alcohol mixes with water. All right, that wraps up our lesson on the structure and properties of alcohols. We talked about how alcohols are defined, how their shape and bonding influence their behavior, and how intermolecular forces, like hydrogen bonding, affect their physical properties. Thanks for watching, and I'll see you in the next Chem Story video.